welcome back. Today we are going to start a new chapter, but possibly this is the most boring chapter we are going to deal with. We are going to talk about AC bridges and measurement of impedance. That means not just resistance, but could be capacitance, inductance or some combination of them. Okay. So, let us begin. So, before we go to AC bridges, we will talk about series and parallel equivalent of a practical inductance or a practical capacitor. Okay. So, when we draw this symbol, this is an ideal inductor. So, this is the symbol of an ideal inductor, where this rule that EMF or voltage is equal to L d I dt. This rule is true with a proper sign. Okay. So, depending on which direction, in which direction you are considering the current and in which direction you are measuring the voltage. So, if I am measuring the current from left to right, this is I t, and if I am measuring the voltage with left side as the positive and right side as the negative side, okay, then we have this relationship V is equal to L d I dt, and this rule for an ideal inductor should be perfectly valid. So, this is an ideal inductor. Okay. But there is no ideal inductor in reality. Why? Because any inductor is after all a coil made up of some conductor, and any conductor is any conductor must have some resistance. Okay. Any coil, any conductor must have some ohmic resistance. I mean, nothing is like a superconductor in reality. So, and practical inductor will always have some resistance, which we can think that this resistance is in series with the inductance. Okay. So, this call this R, call this L, and then the relationship between the current and voltage, you can write it as once again, if I take this side as my positive reference, this side as my negative reference, then we can write that V t is equal to L d I dt plus R I. Okay. So, this is a practical inductor, and we also know that for AC, where I is sinusoidally varying. Okay. So, for special case AC, perfect pure sinusoidal AC, okay. So, that means these voltages and currents and voltages are all like sin omega t cos omega t, pure AC with angular frequency equal to omega. Omega, the unit should be radian per second. Then this relationship we can write using phasors, like V will be equal to j omega L this is the impedance of this inductor, plus R, this is the resistance, multiplied by I, where V and I, these are phasor quantities, and this is the impedance of the inductor. So, this is what we all know. And here this resistance which is in series is quite intuitive. It is easy to understand why do we have this resistance. This is because any conductor, any coil must have some resistance, some ohmic resistance, which is intuitively should be in series with the inductance. Okay. But now what I am going to show you is that this an inductor, pure inductor in series with a pure resistance, okay, call this LSRS. S stands for series because these two are in series, is always equivalent to another circuit where we have this inductor in parallel with a resistance. Call this LP and RP, P because they are in parallel. So given a series combination of a particular value of LS and RS, we can always find a value of LP and RP such that these two circuits are equivalent. Equivalent in the sense the impedance between these two terminals and the impedance between these two terminals is same. Okay. So, this is series parallel equivalence for an practical inductor. Now, how can we find the value of LP and RP if LS and RS are given or vice versa? That is very easy. So, consider this LS in series with RS. So, we can write the total impedance ZS is equal to J omega LS plus RS. Okay. And here for this circuit we can write ZP is equal to the total impedance of this should be 1 over RP plus 1 over J omega LP. Now, suppose this LS and RS are given and we want to find RP and LP. Now, these two to be equivalent, we need ZS and ZP to be equal. If these two circuits are equivalent, so from equivalence we can write that ZS should be equal to ZP, okay, which implies J omega LS plus RS, this should be equal to ZP. Now, in place of ZP we can simplify this and write, so it will be J omega LP by RP plus J omega LP. Okay. So, if you simplify this, you will get this. Okay. Now, from this we can write, so let me take an inverse of this. So, 1 over this will be 1 over this. So, we can write 1 over RS plus J omega LS, this should be equal to RP plus J omega LP whole divided by J, I will have an RP also here, J omega LP RP. Okay. So, now from this what can we write? So, we can let us multiply here with Rs minus j omega Ls in the numerator as well as in the denominator. So, the denominator will become Rs square and minus this term square. So, minus j square omega square Ls square. Now, minus j square is same as plus, because j is root over minus 1, and the right side will be, so if I divide Rp divided by this, so I will have 1 over j omega Lp, this is the first term, plus the second term will be j omega Lp and j omega Lp will cancel, I will have 1 over Rp. Okay. So, basically this side is now the admittance, okay, of the second circuit of this Rp parallel j omega Lp, and this side is actually the admittance of this circuit. So, 1 over impedance is the admittance. Okay. Now, from this what can we write? So, now let us equate the real part with the real part here and the imaginary part of this side with the imaginary part here. So, we will have, so real part is Rs divided by Rs square plus omega square Ls square. So, this will be equal to the real part, which is 1 over Rp, and the imaginary part let us equate. So, we have minus j omega Ls divided by Rs square plus omega square Ls square. This will be equal to the imaginary part here, which is 1 over j means minus j divided by omega square Lp square. Now, this minus j and this minus j you can ignore. So, this implies actually is that Rp is equal to Rs square omega square Ls square divided by Rs, and from here we can write Lp so let us, I think this should be there is no square there, right. So, this is j omega Lp, okay. So, always I suggest that you check my calculation. If I do any mistake, you just correct it yourselves. Okay. So, here from this we can write Lp is equal to Rs square plus omega square Ls square whole divided by omega square Ls square. Okay. So, given Rs and Ls, we can thus find Rp and Lp such that the parallel combination of Rp and Lp will be same or equivalent to the series combination of Rs and Ls. Note that the value of Rp and Lp depends on the frequency omega. Okay. So, this equivalence will be true for a particular frequency, whatever frequency you choose. It is not true for all frequencies. Okay. So, for say 50 hertz, if you get some value of Rp and Lp, for 100 hertz the value of Rp and Lp will be different. Now, let me just give you a small homework. which is very easy to do. So, in here we have found the value of Rp and Lp given value of Rs and Ls. Your homework will be find the value of, say, Rs and Ls from the value of, or from, if the value of Rp and Lp is given, from the given value of Rp and Lp. Okay. So, this is a small exercise I would like you to practice. Okay. So, now next thing we are going to talk about is capacitance. Capacitors. Now, an ideal capacitor, which we denote with just this symbol, or maybe sometimes like this. Okay. For this, no current can actually flow through one plate to the other through this dielectric, because this is a perfect insulator. Okay. So, this is an ideal capacitor. Okay. And for this, the relationships like C is equal to Q by V, from which we get V is equal to ddt of V will be equal to 1 over C I T is true. Okay. This is perfectly true for an ideal capacitor. Okay. And where the current that flows is this I T or this I T. No current goes through the insulator. It flows only from outside to one plate and from the other plate to outside. And the voltage that we are referring here is this voltage. Let me draw it here, Vt, with this side positive and this side as the negative reference. Okay. So, this is an ideal capacitor. Now, a practical capacitor will always have some leakage from one plate to the other through the dielectric. Okay. So, a practical capacitor will always have some leakage current flowing from, say, this side to this side. And how do we model that leakage current? By giving a path for the leakage current, path or a conductance in parallel to this capacitor. So, this is a conductor. Resistance and conductance are equivalent, 1 over resistance is conductance. So, we are giving some conductance, non-zero conductance, okay. So, non-infinite resistance such that some current can flow from here to here. So, this is the model of a practical capacitor, which is a parallel combination of a ideal capacitor with a resistor. Okay. So, and here the what is the relationship between V and I? Okay. So, for that let us first find the impedance of this circuit. Okay. So, and let us take for simplicity, let us take for pure AC with angular frequency omega. Okay, so this part will have an impedance of called, okay, if this capacitance is Cp, if this resistance is Rp, P because they are in parallel, then the impedance of this capacitor is 1 over j omega Cp. Okay, so this is the impedance, and Rp is same as Rp. The impedance of resistance is Rp. So, the impedance Zp, or instead let us write Yp, which is the admittance, which is 1 over Zp, because in this case it is easier to write in or think in terms of Yp. So, this we can write the admittance of this, which will be 1 over impedance, that is j omega Cp, plus the admittance of this, which is 1 by Rp. So, this is the total admittance of this circuit, and therefore, now you can write V is equal to Z P. So, V is the phasor, I is the phasor, or you can write this as V multiplied by Yp is equal to I. Okay. So, this is the relationship between voltage and current. Now, I am claiming that any such practical parallel combination of capacitor and resistor is always equivalent to a capacitor in series with a resistor, where I will denote the value as Rs and Cs respectively, S for series. Now, so my claim is that any such parallel combination is always equivalent to a series combination. Now, how can we find the equivalent series combination? Once again the same trick. So, we have to equate the impedance of this with the impedance of this circuit. So, we can write, so for this we can write Zs, okay, which is the series combination of these two. So, this is Rs plus 1 over j omega Cs. Okay. So, this is the admittance, and now for these two circuits to be equivalent, we can write that Zp should be equal to Zs. Okay. Now, Zp is 1 over Rp, or we can also write it this way, Yp is same as Ys. Now, given the values of Yp, Cp and Rp, we can always find the value of Rs and Cs. Similarly, we can do it in the other way. Given the value of Rs and Cs, we can find the value of Cp and Rp. Now, let us do it this way. Say the value of Cp and Rp given, and we want to find Rs equal to how much, Cs equal to how much. Okay. So, you have to just manipulate this equation. We have to do it in a way such that it becomes easy. Okay. So, let us first write it in terms of admittance, or maybe in terms of the, yes, I think it will be easier if we do it in terms of admittance. Okay, so we can write Yp is equal to j omega Cp plus 1 over Rp, and Zs 1 over Zs is Ys. So let's write okay. Now, or let's do it in other way. So let's write it in terms of impedance. Let's see whichever is easy. So 1 by j omega Cp plus 1 by Rp, this is same as Rs plus 1 by j omega Cs. Okay, so this is the impedance, this is also the impedance. So from this we can write j omega Cp Rp, j omega Cp Rp plus 1, and here we have Rp, and then let's multiply this with Rp times j omega Cp Rp minus 1 whole divided by, so this will be square of this minus square of this. So we'll have omega square Cp square Rp square, and j square is minus 1. Now let's equate the real and imaginary parts. So Rs, this is the real part, will be same as the real part here, and here the real part is, so we have minus minus plus Rp divided by 1 plus omega square Cp square Rp square, and from the imaginary part we can write 1 by j omega Cs, this will be equal to minus j omega Cp Rp square minus j omega Cp Rp square, j omega Cp Rp square whole divided by 1 plus omega square Cp square Rp square. Okay, and from this we can write, so this 1 over j is same as minus j. So then we can write this omega, you can take from left to right side, and then it becomes 1 over Cs is equal to omega square Cp Rp square whole divided by 1 plus omega square Cp square Rp square. Okay, so you can find the value of Cs. Now for you the homework will be, given the value of Rs and Cs, find Rp and Cp. Here we have found value of Rs and Cs from Rp and Cp. Your task is opposite. Okay. Now in this class we will define two more terminologies. Q factor and D factor. This will be the last topic for this class. So, generally the word Q stands for quality. Okay. So, this is like a quality factor, or you can call it, I often call it, this is a goodness factor. It is a measure of measurement, it is a measure of goodness, how good something is. And D stands for dissipation factor. I often call it, this is the degradation factor or a badness factor. Now, a small note is that the term Q factor in electrical engineering is often used in multiple contexts. It has several definitions in several different contexts, like in the context of filters, in the context of resonance circuits, and also in the current context which we are discussing. So, you should not get confused, because unfortunately the same name is used in different cases, different scenarios. Okay. Now, this quality factor is normally used for a practical inductor, although you can extend this thought for capacitors as well, but this is normally used for stating how good an inductor is, and this is D factor is normally used for a practical capacitor to state how bad a practical capacitor is. Now, if we think of a practical inductor, which is always can be modeled as a series combination of some pure inductance and a pure resistance, then the measure of goodness is equivalent to the measure how ideal this inductor is. Okay. So, this goodness factor or Q factor will tell us that how close this practical inductor is to an ideal inductor. When it will be good, then it will be good only if this RS is small compared to the value of the inductance. Okay. So, goodness implies RS should be small compared to the impedance of this part j omega Ls, or if you consider the magnitude only, then you can forget the j. So, this is the magnitude of the impedance of this pure inductive part, and this is due to the coil resistance. There could be other factors too, which we will talk about later. So, this impedance actually not only the coil resistance, it also reflects other losses like core loss, etc. We will talk about that later. Right now, ignore that. Okay. So, therefore, we can write that Q factor is the ratio of omega Ls by Rs. If Rs is small, then this term will be large. So, quality will be better, it will be better, and alternatively if Ls is large, then also the quality will be better. So, this is how you can remember this. Okay. Now, so this is in terms of so this is quality factor in terms of LS and RS. Now, if we go back, we have seen that any LS RS series combination can always be written as, can always be modeled as an LP RP parallel combination, such that the value of LP and RP is like this. So, I made a silly mistake here. This does not have a square here. Okay, this is omega LS, and omega square is because of this omega. LS should not have any square. Okay. Okay. Now, from here we say that RP by LP, if we compute this quantity RP by LP, then this will be same as, so these two terms are same, so they will cancel. We will have 1 over RS, RP is proportional to 1 over RS, and in place of LP we can write this as omega square LS. Okay. So, now if we use this, let me multiply omega here and omega here, which will imply that I cancel 1 omega, and therefore, you see that we have omega LS by RS is same as RP by omega LP. Okay. And this is nothing but the Q factor which we have defined now. Quality factor is omega LS by RS, and this is same as RP by omega LP. Therefore, so we can write it like this as well. Okay. So, in the parallel combination, Q factor will be better if parallel resistance is higher compared to the inductance. Parallel resistance higher means no current will flow through the parallel path of this inductor. Okay. So, this is the definition of Q factor, quality factor, and the way to remember it, you remember that quality is a measure of goodness, and goodness means how close this practical inductor is towards an ideal inductor. An ideal inductor should have no resistance in series. So, RS should be small compared to omega LS. So, RS here should be small, omega LS should be high. Similarly, D factor, this as I said is a badness factor or degradation factor you can call, is normally used for a practical capacitor, which is always lossy or leaky. Some current always flow through the dielectric, which we model using this parallel resistance. Okay. So, now the badness is equivalent to how far this combination, this CPRP combination is from a ideal capacitor. So, badness will be 1 over goodness, and now goodness will imply how how ideal this combination is, which means this Rp should be very high, so that no current can leak through this resistance. The conductance should be very small, or this resistance should be very high. So, goodness means the conductance, that means 1 over Rp, should be very high. Compared to this conductance, and this conductance is j omega Cp. Okay. So, therefore, the D or the badness factor will be given by, so it will be bad if this Rp is small. If Rp is small, more current flows. So, therefore, we have it in the denominator, and it will be also bad if this conductance of call that susceptance of this part is low. Okay. If this is also low, then we write it as like this. Okay. J you can ignore, because we are talking in terms of the magnitude only. So, this is the dissipation factor. Okay. Now, this dissipation factor is in terms of Rp and Cp. Now, we know that this is always equivalent to some Cs, Rs in series. What will be the value in terms of Cs and Rs? That is your homework. Okay. So, in this video, in this class, we have learned two important concepts. Number one, series and parallel equivalence of a practical inductor or a practical capacitor, and how to compute the series parameters if the parallel parameters are given, or how to compute the parallel parameters if the series parameters are given. This is one thing we have learned, and the other thing which we have learned is these two terms, new terms, Q factor and D factor. The way to remember it is, remember that Q factor means quality factor, which is a measure of goodness. Normally, it is used for inductors, and D factor, dissipation factor, is a badness factor, and therefore, Q factor defines how close an practical inductor is to an ideal inductor, and D factor signifies how far a practical capacitor is from an ideal capacitor. Thank you.